Welcome to the IEEE 5G Transmissions Podcast, an IEEE Future Directions Digital Studio production. In this podcast installment, we talk about the main transformative aspects of 5G with Dr. David Soldani. Dr. Soldani is an IEEE Senior Member and Associate Editor-in-Chief of IEEE Network Magazine. He is also the head of 5G technology, end-to-end and global, for Nokia Germany, and is an industry professor at the University of Technology in Sydney, Australia. The assumptions and views reported herein are solely those of Dr. Soldani and do not necessarily represent those of Nokia.
5G, defined as the international mobile telecommunications for 2020 and beyond, will expand and support diverse user scenarios and applications with respect to current mobile network generations, which are purposed primarily for voice, mobile internet, and video experience. There are basically three agreed scenarios in 5G. First is about enhanced mobile broadband experience, addressing human-centric use cases for access to multimedia content, services, and data. The second scenario is on ultra-reliable, low-latency communications with strict requirements, especially in terms of latency and reliability. The third scenario is on massive machine type of communications, which are for a very large number of connected devices and typically transmitting a relatively low value of non-delay sensitive information. 5G technologies will efficiently enable new secure, dependable, ultra-reliable, and delay-critical services to everyone and everything, such as cognitive objects and cyber physical systems. Now, to realize this vision, 5G capabilities will include a new flexible and efficient wireless interface, access schemes, and other enabling wireless and network technologies, as well as a new plastic network architecture supporting multi-tenant and new route models. With network slicing, different end-to-end logical networks with isolated properties are provided and operated independently. This enables operators to support different use cases with device able to connect to multiple slices simultaneously and monetize network slice instances as a service. Two architecture options are possible. The radio access will be based on new radio in a standalone configuration of 5G systems, or non-standalone new radio in an evolved packet system, which is a dual connectivity 5G system deployment with an evolved Ultra as the anchor radio access technology, and new radio as the secondary radio access technology in a non-standalone configuration in evolved packet system. 5G is expected to increase spectrum efficiency and support contiguous, non-contiguous, and much broader channel bandwidth than available to current mobile systems. 5G radio will be the most flexible way to benefit from all available spectrum options from 400 MHz to 90 GHz, including licensed, share access, and unlicensed FDD and TDD modes, including supplementary uplink, narrowband, and wideband allocations. Millimeter wave spectrum above 20 GHz can provide bandwidth up to 1 or 2 GHz, which offers data rates up to 20 gigabit per second, and extreme mobile broadband capacity. The high bands are mostly suitable for local usage, such as mass events, indoor and outdoor hotspots, and for fixed wireless access. Spectrum at 3.5 GHz 4.5 gigahertz and 4.9 gigahertz will be used for 5G coverage and capacity in urban areas, reusing the existing sites, possibly. At those frequencies, the bandwidth can be up to 100 megahertz per operator and even up to 200 megahertz with the refarming of some of the existing bands. In fact, 5G coverage at 3.5 gigahertz, when using massive MIMO beamforming, can be very similar to the one attained using the LTE 1800 or 2100 megahertz. Low band below 1 gigahertz are needed for wide area rural coverage, for high reliability and deep indoor penetration. Extensive coverage is important for new use cases such as the IoT and critical communications. The low band could be 700 megahertz, which is available in many countries, or not 100 megahertz, today mostly used by 2G and 2G systems. In the USA, another option for 5G low band is 600 megahertz. The new radio is for all spectrum options. To this end, 5G supports a flexible numerology, which consists of different subcarrier spacing, nominal cycling prefix, and transmission time intervals or scheduling intervals, depending on bandwidth and latency requirements. Subcarrier spacing of 15 kilohertz to 120 kilohertz and the corresponding cycle prefix of 4.7 to 0.6 microseconds and scheduling interval of 1 millisecond to 0.125 milliseconds are defined for different carrier components, which may vary from 5 megahertz to 100 megahertz below 6 gigahertz and from 50 to 400 megahertz above 6 gigahertz. For optimal radio performance, the higher the frequency, the higher the allowed carrier component and subcarrier spacing, the lower the corresponding cycling prefix and scheduling period. If you consider a typical 5G deployment at 3.5 gigahertz band, the bandwidth could be 40 to 100 megahertz, the subcarrier spacing 30 to 60 kilohertz, and minimum scheduling period of 0.125 milliseconds. The corresponding numbers in LTE are 20 megahertz bandwidth, 15 kilohertz subcarrier spacing, and 1 millisecond scheduling period. In narrowband cases where low latency is required, the so-called mini slot can be used in 5G, where the transmission time may be reduced to 2, 4, or 7 OFDM symbols. And it's also possible to combine multiple slots together. Massive MIMO will be definitely an integral part of 5G from day one, including common and control channels with beamforming and tracking. With massive MIMO, the number of transmitting antenna elements is much higher than the number of MIMO streams or layers. In practice, massive MIMO means that the number of controllable antenna elements is more than 8. 5G radio will support 8 layers single-user MIMO or 16 layers multi-user MIMO in the downlink, and 4 layers single-user MIMO in the uplink, with the possibility of dynamic switching in both directions. Multi-user MIMO means that parallel MIMO data streams or layers are transmitted to different users at the same time frequency resources. A typical example of 16-layer configuration is 2 layers per terminal multiplied by 8 terminals multi-user MIMO. Beamforming offers the advantages that the same resources can be reused for multiple users in a cell. It allows space division multiple access, SDMA, maximizing the number of supported users within that sector. It minimizes interference and increases cell capacity. As a result, massive MIMO and active antenna technologies give higher spectral efficiency, and provide much more capacity on existing base station sites. The technology can also enhance link performance and increase the coverage area. The 5G radio design is really fully optimized for massive MIMO, using three basic techniques for forming and steering beams. We have digital beamforming, analog beamforming, and hybrid beamforming. Digital beamforming, where each antenna element has a transceiver unit with the adaptive TRX weights in the baseband, enabling frequency-selective beamforming. Digital beamforming boasts capacity and flexibility, and it's mostly suited to bands below 6 GHz. Analog beamforming implements only one transceiver unit and one RF beam polarization. Adaptive TRX weighting on the RF is used to form a beam. This is best suited for coverage at higher millimeter wave bands and offer low cost and complexity. Hybrid beamforming is a combination of analog and digital beamforming. When some beamforming is in the analog domain, the number of transceivers is typically much lower than the number of physical antennas, which can simplify implementation, particularly at high frequency bands. This technique is suited to bands above 6 GHz. The radio interface protocol stack is also optimized for cloud and distributed computing, with a flexible front-haul split between higher layer protocols, PDCP and RLC, and lower layer PIA entities, using the enhanced common public radio interface. This will allow to relax the transmission capacity and the utilization of Ethernet. For example, assuming 100 MHz band, a 3-sector site with 64 TRXs, massive MIMO, and 16 layers, the interface between the radio unit and edge cloud would require 1 terabit per second window split using a CPRI interface, 150 gigabit per second with low layer split and enhanced CPRI interface, and 1 to 10 gigabit per second with higher layer split. The latency with low layer split is expected to be below 0.1 millisecond, as with CPRI, and 5 milliseconds with higher layer split, which is still satisfactory for ultra-reliable low latency communications. Now, compared to LT1800 with 2x2 MIMO configuration as baseline, 5G gives 10 to 20 additional more capacity, being 2 to 4 times more spectrally efficient. For example, LTE with 20 MHz band achieves 40 megabit per second cell throughput, which corresponds to a spectrum efficiency of 2 bit per second per hertz. 5G with massive MIMO beamforming at 3.5 GHz and 100 MHz band reaches 400 to 800 megabit per second cell throughput, corresponding to a spectrum efficiency of 4 to 8 bit per second per hertz. In addition, the radio interface latency with the 5G is also dramatically reduced compared to the previous releases. The target is 1 millisecond in idle and connected mode with and without uplink resources allocated. 5G solutions to low latency are, for example, shorter transmission time interval, connected active state, and contention-based uplink. But of course, 5G is not only about radio. Additional benefit will come with the introduction of the 5G core, or 5GC, which supports many new enabling network technologies. For example, the 5GC is characterized by a layered and service-oriented architecture, with a control plane and user plane split and shared data layer for subscription, state, and policy information. It also supports user plane session continuity while the terminal moves across different access points, interworking with untrusted non-TCP/IP access, a comprehensive policy framework for access, traffic steering, switching and splitting, and wireless wireline convergence. Other fundamental 5G enabling technologies end-to-end are, for example, flow-based QoS with a much higher level of granularity than LTE, which is currently limited to the base service concept. Multi-connectivity, where the 5G device can be connected simultaneously to 5G, LTE, and Wi-Fi, offering a higher user data rate and more reliable connection. Terminal-assisted network slicing and end-to-end network management and orchestration with inbuilt support for cloud implementation and edge computing. 5G network slicing comes along with new information and role models and slice management functions responsible for the management and orchestration of network slice instances. A network slice instance consists of one or more network slice subnet instances of physical network function and or virtualized network functions. Within this framework, three main roles are defined, namely the communication service customer, for example, consumer, enterprise, vertical, CSP, etc., who may use communication services from a communication service provider. The communication service provider builds its offering on top of network slice services from network operator and virtual infrastructure services from the virtual infrastructure and data center service providers. And the physical and virtual network functions composing the network slice instances end-to-end may be provided by the network equipment vendors, network function virtualization infrastructure suppliers, and hardware suppliers. It's of course intended that an organization may play one or several roles. The newest CSP offering, so the operator offering, enabled by the 5G slicing, is Network Slice as a Service, and SaaS. Like cloud computing, SaaS, IaaS, and the PaaS model, the communication service customer, also denoted as the tenant, so the tenant may compose, order, and pay one or more network slice instances based on its utilization, service level agreement, and for example, in terms of latency, throughput, and reliability, and value-added services. In practice, 5G will support three basic models for network slicing, depending on the tenant's degree of slice control, which may go from monitoring only the KPIs related to the signed SLAs, changing the configuration of the deployed slice instances, to chaining on physical and or virtual network functions. The partitioning model may be combined with the layering model to provide joint horizontal and vertical offerings. In slice partitioning, the orchestration of resources and capability from an end-to-end service requirement perspective must be horizontally federated and vertically coordinated through policy and standardized interfaces and APIs. The end-to-end systems in 5G will consist of 6 main domains, from terminal to the data network and service application. A, the terminals, supporting network slice selection assistant information to request specific slice instances based on the communication services in use. B, the access, ELT new radio units with Ethernet front haul, ECPRI, or Ethernet mid haul for low latency and latency intensive services, respectively. C, aggregation, radio clouds with their own software-defined network controllers and virtual infrastructure managers. D, mobile core, a core cloud with own SDN controller and virtual infrastructure manager interconnected to the radio clouds by IP routers and WAN SDN controllers. E, network slice management and orchestration, an end-to-end service orchestrator for the embedding of network service descriptors on top of self-organizing network and VNF manager functions. And F, data layer and application enablement. For example, IoT and customer experience management platforms for running applications on top of efficient network slices for public safety, digital health, mobility, industry automation, smart city, and so forth. Artificial intelligence, in terms of descriptive, predictive, and prescriptive analytics, will find application in three main areas. First, self-organizing networks. Here we are talking about key capabilities, algorithm, architecture attributes within the different domains, run, core, transport, so forth, to enable the right flexibility and trade-offs for operators to efficiently exploit slicing. Second, data and application layers. And this is about big data analytics, structured data analytics, text analytics, web analytics, multimedia analytics, network analytics, mobile analytics, and third, the data layer platform for IoT and customer experience management. Now, to realize our 5G vision, or actually the vision I've just presented, spectrum must be made available first. Global standards next, and regulation must follow. It's also necessary a massive investment from industry, especially from connectivity service providers, which are currently our operators.
Thank you for listening to this edition of the IEEE 5G Transmissions podcast. Discover more about the IEEE 5G initiative and inquire about participating in this effort by visiting our web portal at 5g.ieee.org.